Hey everyone, welcome to a lesson on solving rational inequalities. In this video, I'm going to work through 5 different rational inequalities with you. By the end of this video, it's my hope that you'll feel much better about solving these types of math problems. Let's get into it. Before we do anything else, it's a good idea to always get 0 alone on the right side. Once this is done, we need to look for some important points. To find our important points, we're going to set the numerator equal to 0 and our denominator equal to 0. Setting our numerator equal to 0 here, we're going to get 5x is equal to 0. Getting x alone, if we divide both sides by 5, we're going to get x is equal to 0. This is going to be one of our important points. Now let's set our denominator equal to 0. So we have x squared minus 9 is equal to 0. Well, we could solve this using square roots. I'm going to factor this by using difference of squares to get you in the mindset of factoring. The value for x that makes this 0 is x equals negative 3, and the value that makes this binomial go to 0 is x equals positive 3. These are 2 more points that are important. Once we have all our important points, we're going to plot them on our number lines. We have negative 3, 0, and positive 3. Since our inequality says greater than or equal to 0, I'm going to put a closed circle on 0 here since x is allowed to equal 0. We're going to have to put open circles on the negative 3 and positive 3 since they're in the denominator. Since there would be vertical asymptotes at positive and negative 3, we have to put open circles on those values. These 3 important points we found divide our number line into 4 different parts. Our first part represents all the numbers from negative infinity up until negative 3. Our second part represents all the numbers from negative 3 to 0. The third part represents any values that are from 0 to positive 3. And our fourth part represents any values from 3 to positive infinity. Our goal is to now find which of these intervals has values that make this rational inequality true. For the first interval of negative infinity to negative 3, I'm going to test the value negative 4. Substituting in, we're going to get 5 times negative 4 divided by negative 4 squared minus 9. 5 times negative 4 is negative 20, negative 4 squared is 16, and 16 minus 9 is going to be 7. Since negative 20 over 7 is a negative value, we know that any number in this interval will create a value that's less than 0. Now let's test a number in this second interval. Between negative 3 and 0, I'm going to test negative 1. 5 times negative 1 over negative 1 squared minus 9. 5 times negative 1 is negative 5. Negative 1 squared is positive 1, minus 9 is going to be negative 8. Negative 5 divided by negative 8 is going to be a positive, so we know everything's going to be positive in this interval. In this third interval from 0 to 3, I'm going to test the value 1. Substituting in, we get 5 times 1 over 1 squared minus 9. 5 times 1 is going to be 5. 1 times 1 is going to be 1. Minus 9 is going to be negative 8. Since 5 divided by negative 8 is going to be a negative value, we know that everything's going to be negative in this interval. In this last interval, we have to test something that's greater than 3. I'm going to test the number 4. Substituting in, we have 5 times 4 on top, and then we have 4 squared minus 9 on bottom. 5 times 4 is going to be positive 20 over 4 squared is 16 minus 9 is going to be positive 7. Since 20 divided by 7 is a positive, we know all the values will be positive in this interval. Now that we know the signs of our intervals, let's see which of them makes our rational inequality true. Remember, we're trying to find when this rational expression is greater than or equal to 0. Since this first interval is negative, that's not going to make it true. The next one's positive, so it does. While this third interval also doesn't work, the fourth interval to the right does. Representing the solutions to this rational inequality, we can say it's from negative 3 to 0, and it's going to be from 3 to positive infinity. The values of x contained in these intervals will make this rational inequality true. Using inequalities, we can say that negative 3 is less than x, which is less than or equal to 0, or x is greater than 3. Let's try another one here. First, you should be happy that the 0 is already alone on the right side. But then you get a little sad here because not only do we have one fraction, but we have 2 now. Before we do anything else, we're going to have to combine these fractions to make one fraction. To rewrite this expression with just one fraction bar here, we're going to need to get common denominators. Notice how our denominator for the left part is x plus 3, and our denominator for the right part is x minus 1. Since they're different, we're going to have to find the LCM of these denominators. First, I'm going to give each of these binomials a hug to keep them organized. Then I'm going to multiply this left fraction here by x minus 1 over x minus 1. Then I'm going to multiply the fraction to the right by x plus 3 over x plus 3. By doing so, we've created common denominators for these fractions. Rewritten as one fraction, we're going to have x minus 1 times x minus 4 minus x plus 2 times x plus 3. This whole thing is going to be written over x minus 1 times x plus 3. To simplify this numerator, we're going to have to distribute to combine like terms. X times x is going to be x squared, x times negative 4 is going to be negative 4x, and negative 1 times x is going to be negative 1x. These will combine to make negative 5x. And this negative 1 times this negative 4 is going to be positive 4. Then we're going to subtract the product of these binomials here. Don't forget to put a parentheses around them since this negative in front applies to everything after it. X times x is going to be x squared, x times positive 3 is going to be positive 3x, and 2 times x is going to be positive 2x. Combined, they'll make positive 5x. And last, we'll do 2 times 3 here is going to be positive 6. Distributing this negative here to each of these terms, we're going to have the new expression of x squared minus 5x plus 4 minus x squared minus 5x minus 6. Now that we finally have no more grouping symbols, we can combine like terms. X squared and negative x squared are going to be canceled out. Negative 5x and negative 5x make negative 10x. And positive 4 minus 6 is going to be negative 2. This is going to be our simplified numerator, and it's going to be on top of x minus 1 times x plus 3. Remember, this whole thing is less than or equal to 0. After all that work, we finally have one fraction. To find our first important point, we're going to set our numerator equal to 0. Adding 2 to both sides here, we're going to get that negative 10x is equal to positive 2. Dividing both sides by negative 10, we're going to get x is equal to negative 1/5. This is one of our important points. Now let's set the denominator equal to 0. We have x minus 1 times x plus 3 is equal to 0. The value that makes this binomial equal to 0 is going to be x is equal to positive 1, and the value that makes this binomial equal to 0 is going to be x equals negative 3. Here are 2 more important points. Next, I'm going to go to my number line and plot these important points down. Here we have negative 3, we have negative 1/5, and we have 1. Since we have an inequality of less than or equal to 0, we know we're going to put a closed circle here on negative 1/5. However, we're going to have to put open circles on negative 3 and positive 1 since they're in the denominator. There are vertical asymptotes located here. Now that we have our important points, we also have our intervals here. We have negative infinity to negative 3 to negative 1/5 with a bracket, negative 1/5 to 1, and 1 to positive infinity. For this first interval here, let's test the value negative 4. Since we don't care about what the actual values are, let's just worry about the signs. Plugging in negative 4 to the numerator, we're going to get negative 10 times negative 4, which is positive 40, minus 2, which is 38. That's a positive value. Plugging in negative 4 to the bottom left, negative 4 minus 1 is going to be negative 5. That's a negative value. And negative 4 plus 3 is a negative value, so this will also be negative. In the denominator, a negative times a negative is a positive, and a positive divided by positive is going to be a positive. That means that all values in this interval will create a positive value. Now let's test a value in our second interval. I'm going to test the value negative 1. In the numerator, negative 10 times negative 1 is positive 10, minus 2 is going to be positive 8. The numerator is going to be positive. On the bottom left, negative 1 minus 1 is going to be negative 2, which creates a negative value. And negative 1 plus 3 is going to be positive 2, which is a positive value. In the denominator, negative times a positive is a negative, and a positive divided by a negative is going to be a negative. Any value in this interval is going to be negative. For our third interval, let's test the value 0. In the numerator, negative 10 times 0 is 0, and 0 minus 2 is going to be negative. Plugging in 0 on the bottom left, 0 minus 1 is negative 1, which is negative. Plugging in 0 to the bottom right, we have 0 plus 3, which is positive. The negative and positive on the bottom make a negative, and a negative divided by a negative is going to be a positive. Everything's going to be positive in this interval. Now let's move to the third interval and test a value like 0. In the numerator, negative 10 times 0 is 0, minus 2, which is going to be negative 2. That's negative. On the bottom left, 0 minus 1 is negative 1, and that's negative. And on the bottom right, 0 plus 3 is going to be positive 3, and that's a positive. On the bottom, negative times a positive is a negative, and negative divided by a negative is going to be a positive. Everything's going to be positive in this interval. In this last interval, I'm going to test a value here like 2. Negative 10 times 2 is negative 20. Negative 20 minus 2 is negative 22. The numerator is going to be negative. On the bottom left, 2 minus 1 is going to be 1. That's positive. And on the bottom right, 2 plus 3 is going to be 5, which is positive. On the bottom, a positive and a positive is going to be a positive, and the top negative divided by positive is going to be a negative. Everything in this interval is going to be negative. Since we want our rational inequality to be less than or equal to 0, this first interval won't work. The second one will. The third one won't. But the fourth one will. Using interval notation, we can say the values for x that make this rational inequality true are negative 3 to negative 1/5, union 1 to infinity. Any values of x that are in these intervals will make this rational inequality true. Using inequalities, we can say negative 3 is less than x, which is less than or equal to negative 1/5, or x is greater than 1. These mean the same thing. Here in example 3, we don't have a 0 isolated to the right side. To get it, we can add x minus 3 over x minus 1 to both sides of this inequality. In doing so, we're going to get x plus 1 over x minus 2 plus x minus 3 over x minus 1. This whole thing is going to be less than 0. Similar to the last example, we need to get common denominators here. First, I'm going to group all our binomials by giving them a nice hug here. And I'm going to multiply this left fraction by x minus 1 over x minus 1, and multiply this right fraction here by x minus 2 over x minus 2. Rewritten as one fraction, we're going to have x minus 1 times x plus 1 plus x minus 3 times x minus 2. This whole thing is going to be on top of x minus 1 times x minus 2. Multiplying these binomials out, this x times x is going to be x squared. X times positive 1 is going to be positive x, and negative 1 times x is going to be negative 1x. These are just going to cancel out. And this negative 1 times positive 1 is just going to be negative 1. Now let's multiply these binomials together here. X times x here is going to be x squared. X times negative 2 is going to be negative 2x, and negative 3 times x is going to be negative 3x. Combined, this negative 3x and negative 2x are going to make negative 5x. Finally, this negative 3 times negative 2 is going to be positive 6. Combining like terms, this x squared and x squared are going to make 2x squared. This negative 5x here is just going to be negative 5x. And this negative 1 and positive 6 are going to just combine to make positive 5. After all that work, this represents our numerator. We're going to write this new numerator over our common denominator. Copying this over, we have 2x squared minus 5x plus 5 all over x minus 1 times x minus 2. This whole thing is less than 0. Now that we finally have one fraction, let's set our numerator equal to 0 in search of some important points. While I'd like to factor, this trinomial is simply just not factorable. Instead, we're going to have to try out the quadratic formula here. When completing the quadratic formula, it's always a good idea to start with the discriminant. The discriminant is the b squared minus 4ac part. The reason why we should start with the discriminant is because if it happens to be negative, there's not going to be any important point here. If it's equal to 0 or it's positive, we know that we will be able to find an important point. Substituting in here, we're going to get negative 5 squared minus 4 times 2 times 5. Negative 5 squared is going to be 25, and 4 times 2 times 5 is going to be 40. 25 minus 40 is going to be negative 15. Since our discriminant is negative here, we're not going to have any real solutions. We found no important points from the numerator. Now let's set our denominator equal to 0 to look for more important points. From this first binomial, we know that x equals 1 is going to be one important point. From the second binomial, we know that x is equal to positive 2 is another. These are our two important points. Here I'm going to place them on our number line. Since both of these important points came from the denominator, we're going to put open circles on them since there are vertical asymptotes here. These 2 points in our number line create 3 intervals. We have negative infinity to 1, we have 1 to 2, and we have 2 to infinity. Let's test a value here for our first interval. I'm going to test 0. Plugging in 0 to the numerator, we should just be left with 5, which is a positive number. Plugging in 0 to the bottom left, we're going to get negative 1, which is a negative number. And plugging in 0 to the bottom right is going to be negative 2, which is a negative number. A negative times a negative is a positive, and a positive divided by a positive is going to be a positive. Everything will be positive in this interval. Now let's test 1.5 in this next interval. Plugging in 1.5 to the top, 1.5 squared is 2.25, and 2.25 times 2 is going to be 4.5. Minus 5 times 1.5 is going to be 7.5. We're going to add 5 here. 4.5 minus 7.5 is going to be negative 3, and negative 3 plus 5 is going to be 2. Our numerator here is going to be a positive value. Plugging in 1.5 to this bottom left here, 1.5 minus 1 is positive 0.5, so that's going to be positive. And plugging in 1.5 to this bottom right, 1.5 minus 2 is going to be a negative 1/2, so that's negative. On the bottom here, positive times a negative is a negative, and a positive divided by a negative is going to be a negative. Everything in this interval is going to be negative. In this third interval, I'm going to test the value 3. In the numerator, we have 3 squared, which is 9, and 9 times 2 is going to be 18, and 5 times 3 is going to be 15, so it's going to be minus 15 plus 5. 18 minus 15 is 3, and 3 plus 5 is going to be 8. the numerator is going to be positive here. Plugging in 3 to this bottom left, 3 minus 1 is 2, which is positive. And plugging in 3 minus 2, which is equal to 1, that's going to be positive on the bottom right. Positive times a positive is positive, and a positive divided by a positive is also going to be positive. Everything in this interval is positive. Since we're looking for values that are less than 0, this first interval does not work, the second one does, and the third one doesn't. The values of x that make this rational inequality true are between 1 and 2. This represents our solutions in interval notation. Using inequalities, we can say 1 is less than x, which is less than 2. This means the same thing. In example 4, we have another rational inequality that doesn't have a 0 isolated on the right side here. For starters, let's subtract 3 from both sides of this rational inequality. When we do that, we're going to get x plus 1 over x minus 2 minus 3 is greater than or equal to 0. If you were thinking that we need to rewrite this using one fraction bar, you're right. Good job. We can rewrite 3 here as 3 over 1. To rewrite 3 with a common denominator of x minus 2, we need to multiply it by x minus 2 over x minus 2. This will be equivalent to 3 times the quantity of x minus 2 over x minus 2. Writing this in the problem, I'm going to write 3 times x minus 2 over x minus 2. Using one fraction bar, we can rewrite this as x plus 1 minus 3 times the quantity of x minus 2 all over x minus 2. This whole thing is greater than or equal to 0. Now let's simplify this numerator by distributing this 3. Here we're going to get x plus 1 minus 3x plus 6 all over x minus 2. Combining like terms here, we have x minus 3x, which is going to be negative 2x, and we have 1 plus 6 is going to be 7. Negative 2x plus 7 is going to be on top of x minus 2, and this is still greater than or equal to 0. Finally, we have one simplified fraction. Yay! Now that we have one fraction and we have a 0 isolated to the right, we can look for our important points. Let's start by setting the numerator equal to 0. We can subtract 7 from both sides here and get that negative 2x is equal to negative 7. Dividing both sides by negative 2, we're going to get that x is equal to 7 halves. This is one of our important points. Now let's set our denominator equal to 0. Adding 2 to both sides here, we can see here that x is equal to positive 2. In this problem, we have 2 important points. 7 over 2 is the same thing as 3 and 1/2. I'm going to put that right here in our graph as 3.5 and put our 2 over to the left of it. Since our inequality is allowed to equal 0, I'm going to put a closed circle on this 3.5. Since our important value of 2 came from the denominator, we're going to have to put an open circle there because there's a vertical asymptote there. Here our 3 intervals are going to be from negative infinity to 2, 2 to 3.5, and 3.5 to infinity. For this first interval, let's test 0. Plugging in 0 to the numerator, negative 2 times 0 is 0, and 0 plus 7 is going to be 7. That's a positive value. Plugging in 0 to the denominator, 0 minus 2 is negative 2, which is a negative value. A positive divided by a negative is going to be a negative, so everything in this interval is going to be negative. For the second interval here, I'm going to test the value 3. In the numerator, negative 2 times 3 is going to be negative 6, and negative 6 plus 7 is going to be positive 1. The numerator is going to be positive. In the denominator, 3 minus 2 is going to be 1, and that's going to be positive. A positive divided by a positive is going to be positive, so everything is going to be positive in this interval. In this last interval, let's test the value 4. Negative 2 times 4 is going to be negative 8, and negative 8 plus 7 is going to be negative 1. The numerator is going to be negative. In our denominator, 4 minus 2 is going to be 2, which is going to be positive. A negative divided by positive is a negative, so everything in this interval is negative. Since we're looking for intervals that are greater than or equal to 0, this first one's not going to work, this middle one will, and this last one won't. In interval notation, the solutions are going to be between 2 and 7 halves. As an inequality, we can say that 2 is less than x, which is less than or equal to 7 halves. Both of these represent our solutions. Here's our final example. Let's get a 0 to the right by subtracting the 5 over x squared minus 9 to the left side. When doing so, we're going to have 2 over x squared minus 4x plus 3 minus 5 over x squared minus 9. This whole thing is going to be less than or equal to 0. To get common denominators to combine these into one fraction, we're going to have to factor these trinomials into denominators so we can see their linear factors. This first fraction is going to factor into 2 over x minus 3 times x minus 1. Our second fraction is going to factor into a difference of squares of x plus 3 times x minus 3. I'm going to leave off the less than or equal to 0 for now. Fortunately, we see that they at least have x minus 3 in common. Unfortunately, the left fraction is missing an x plus 3, so we have to multiply the left fraction by x plus 3 over x plus 3. And the fraction to the right is missing an x minus 1, so we have to multiply the top and bottom by x minus 1. Our left numerator is going to be 2 times the quantity of x plus 3, and the right side is going to be 5 times the quantity of x minus 1. Don't forget this minus sign here. This whole thing is going to be over x plus 3 times x minus 3 times x minus 1. Now that we have one fraction, let's simplify the numerator here. By distributing this 2 to the x and 2 to the 3, we're going to have 2x plus 6. And by distributing this negative 5 to the x and the negative 1, we're going to get minus 5x plus 5. Combining this negative 2x and negative 5x, that's going to be negative 3x. And combining this positive 6 and positive 5, that's going to be positive 11. Negative 3x plus 11 is our numerator, and x plus 3 times x minus 3 times x minus 1 is our denominator. Remember, this whole thing is less than or equal to 0. Now we can finally look for important points by setting the numerator equal to 0. Here we have negative 3x plus 11 is equal to 0. Subtracting 11 from both sides here, we're going to get that negative 3x is equal to negative 11. Dividing both sides by negative 3, we're going to get that x is equal to 11 thirds. This is one of our important points. Now let's set the denominator equal to 0. We have x plus 3 times x minus 3 times x minus 1 is equal to 0. The values that make this equal to 0 are x equals negative 3, x equals positive 3, and x equals positive 1. In this problem, we have 4 important points. Putting them on our number line, I'm going to put negative 3 over here, 1 over here, 3 over here, and 11 thirds over here. Remember, 11 thirds is the same thing as 3 and 2 thirds. Let's see if we should have open circles or closed circles. Since 11 thirds came from our numerator and our inequality says less than or equal to 0, we know we have a closed circle on 11 thirds. Since all the other important points came from the denominator, we need to put open circles here because they're vertical asymptotes. Here we have 5 intervals of negative infinity to negative 3, negative 3 to positive 1, positive 1 to positive 3, positive 3 to 11 thirds, and 11 thirds to infinity. For this first interval on the left, let's test negative 4. In the numerator, negative 3 times negative 4 is 12, and 12 plus 11 is going to be 23. That's positive. On the bottom left, negative 4 plus 3 is negative 1, so that's negative. In the middle here, negative 4 minus 3 is negative 7, and that's going to be negative. And on the bottom right, negative 4 minus 1 is negative 5, and that's negative. On the bottom, a negative times a negative times a negative is a negative, and a positive divided by negative is just going to be negative. Everything in this interval is going to be negative. For the second interval here, let's test 0. Negative 3 times 0 is 0, and 0 plus 11 is going to be 11. The top is going to be positive. On the bottom left, 0 plus 3 is going to be 3, and that's positive. In the middle, 0 minus 3 is negative 3, which is negative. And in the bottom right, 0 minus 1 is negative 1, which is negative. On the bottom, a positive times a negative is a positive, and a positive divided by a positive is going to be positive. Everything's going to be positive in this interval. In this third interval, let's test the value 2. Negative 3 times 2 is negative 6, and negative 6 plus 11 is going to be 5. That's going to be positive. On the bottom left, negative 2 plus 3 is going to be 5, and that's positive. In the middle, 2 minus 3 is negative 1, so that's negative. And on the right, 2 minus 1 is positive 1, which is positive. On the bottom, a positive times a positive is going to be negative, and a positive divided by negative is going to be negative. Everything's negative here. In this fourth interval here, let's test 3.5. Negative 3 times 3.5 is going to be negative 10.5, and negative 10.5 plus 11 is going to be positive 0.5. The numerator is going to be positive here. On the bottom left, 3.5 plus 3 is going to be positive 6.5, so that's positive. In the middle, 3.5 minus 3 is going to be positive 0.5. And on the bottom right, 3.5 minus 1 is 2.5, which is positive. Since everything's positive here, this interval will be positive as well. In this last interval, I'm going to test the number 4. Negative 3 times 4 is going to be negative 12, and negative 12 plus 11 is going to be negative 1. The numerator is going to be negative. 4 plus 3 is 7, so the bottom left is going to be positive. 4 minus 3 is going to be positive 1, which is positive. And 4 minus 1 is 3, which is positive. On the bottom, we're going to have a positive, and a negative divided by positive is going to be a negative. This last interval has a negative value. Let's recall that we're looking for values that are less than or equal to 0. This first interval is going to work. The second one's not. the third one is, the fourth one's not, and the fifth one is. Using interval notation, we can say negative infinity to negative 3, 1 to 3, and 11/3 to infinity. Remember to put a bracket on 11/3. This is our interval notation. As an inequality, we can say x is less than negative 3, or 1 is less than x, which is less than 3, or x is greater than or equal to 11/3. These are the intervals that make these rational inequalities true. I hope you found this video useful in understanding how to solve rational inequalities. Keep up the good work, and I'll see you in the next one.